Hi everybody and thank you for joining this presentation. I'd like to quickly introduce myself. My name is Alessio Moreschini and I'm a doctoral candidate at Sapienza University of Rome and Université Paris-Saclay. Today I'd like to discuss feedback passivation under sampling. This is joint work with my supervisor Salvatore Monaco and Dorotheo Mancio and together with Mattia Mattioni from Sapienza University of Rome. Let's begin with some general motivations on this work. Feedback passivation is at the basis of several passivity-based control strategies such as backstepping, feed-forwarding, energy balancing, interconnection damping assignment, and many other passivity-based control strategies. They generally aim to find feedback and an output function for which passivity holds with respect to a suitably defined storage or energy function to achieve stabilization at the desired equilibrium point. Nowadays, as we are in the middle of the data era, sample data control is very challenging because of its practical interest in computer-oriented design. During my talk, we addressed the following question. If the feedback passivation is ensured in continuous time, is it possible to preserve feedback passivation under sampling? So this is the menu for today. First, I'm going to recall the notion of feedback passivation and passivity in discrete time, and then I will share with you the problem statement under sampling. Next, first we give the main result and then we apply the methodology to a damped pendulum system, comparing the results with a more standard emulation feedback. Finally, we end the presentation with some perspectives and concluding remarks. Let's start. A continuous time input affine dynamics is said to be feedback passive if there exist functions gamma, hd, and a positive semi-definite function sd such that the feedback U makes the closed loop dynamics passive with respect to the output Y and storage function SD, so that the dissipation inequality in red holds true for any t and the initial condition x0. If the system is zero-state detectable, then x star, which is the isolated minimum of the storage function SD, can be asymptotically stabilized through this negative output damping injection feedback V, where K is a positive constant defining the damping improvement. On the other side, the discrete time system is said to be passive if there exists a positive semi-definite storage function SD verifying for all xk and uk the dissipation inequality in the whole time horizon from 0 to k, and equivalently in two time steps between xk plus 1 and xk for all k greater than 0. It is important to stress that, differently from the passivity in continuous time, a necessary condition to achieve passivity in discrete time is to provide an output function depending on the control variable u. In this presentation, we refer to discrete time system issued from the uniform sampling of the continuous time system. The continuous time system is interfaced with the digital environment through the converter devices such as samplers and zero-holder-old. The sampler aims at reproducing a discrete sequence of signals of the continuous time state xt and output yt at the sampling instance t equal k delta, where delta is the sampling period of fixed length. Accordingly, the control input u is a discrete sequence of signals which will be injected into the sample data framework in order to control the continuous time system and is converted to a piecewise constant signal through the zero-holder-old device. In this framework, a sample data system admits an equivalent state space representation of this form given in red, so recovering for each delta a discrete time model that is by construction parameterized by the sampling period delta. Then the question is, does feedback passivation of the continuous time dynamics imply feedback passivation of the sample data model? More in particular, assuming the continuous time system feedback passive with storage function SD, the objective is to find a digital control u equal gamma delta plus b and find an output mapping y depending on delta, making the closed loop system passive with respect to the output mapping and the same continuous time storage function, so recovering the passivity condition here. Then, asymptotic stabilization to the desired equilibrium point x star follows from the damping injection of the passive output, solving the implicit equality in V with damping improvement k greater than 0. So the solution to this question is based on the input SD matching, which consists on the design of a digital feedback ensuring matching of the storage function behavior at the sampling instance along the ideal continuous time feedback. More in detail, as given by the reference 5, assume the continuous time system passive, then there exists a unique solution UK equal gamma delta to the input SD matching equality, which ensures that the energy variation between two steps is negative semi-definite, where gamma delta admits a series expansion in power of delta of this form here, and where the first term gamma x is the continuous time feedback. Therefore, the input SD matching feedback gamma delta ensures matching of SD at all the sampling instants along the closed loop continuous time system. Moreover, under the feedback U equal gamma delta plus V, where V is the new external input, due to the solution to the input SD matching equality, one gets that the variation between two time steps of the storage function verifies the passivity condition with respect to a suitable defined output. Finally, gamma delta can be iteratively computed term by term up to a desired order of delta, so getting for the first terms the following expressions here. One may notice that for delta converging to 0, the sample data solution converges to the continuous time one. Then we are ready to state the main theorem. Assume continuous time system feedback passive with gamma, SD, and HD. Then, under feedback U equal gamma delta plus V, where gamma delta is the solution to the input SD matching equality and V is the new external input, the sample data system is passive and verifies the passivity condition with respect to an output function HD of this form here. In addition, if the continuous time system is zero state detectable, then the sample data system with HD delta is zero state detectable and U equal gamma delta plus B makes the equilibrium X star asymptotically stable in closed loop with V solution to the implicit damping equality here given. Some comments arising from the result. Feedback passivation undersampling is ensured with respect to a new output HD depending both on the external input V and sampling period of delta. The defined output admits an expansion in power of delta of this form here given in red. Moreover, sample data damping injection is performed with an external control V as the solution of the implicit damping equality, admitting also an expansion in power of delta of this form here, so showing again that the damping injection recovers the continuous time solution in first approximation. So let's apply the results on the theorem to an example. Consider the dynamics of the pendulum system given in the top right figure, where H denotes the Hamiltonian function, describing the sum of the kinetic and the potential energy of the system. Assume that we want to stabilize the pendulum at a desired angular position Q star, which is the angular displacement between the pendulum and the vertical axis. The continuous time model is feedback passive through the IDA PBC feedback U equal gamma plus B, with gamma being the control that shapes the energy of the closed loop system and which ensure passivity with respect to the desired storage function HD having an isolated minimum in X star and verifying the passivity condition along HD with V being the damping injection feedback. Exploiting the result and for sake of presentation, we consider the approximate first-order digital control. Indeed, under sampling, one computes the approximate first-order digital control of this form, where gamma 1 is the first-order approximation of the input HD matching equality. Then, feedback passivation under sampling is ensured with storage HD of the continuous time system and pacifying output given in red, which verifies the following dissipation inequality. In addition, when V is computed as the solution of the implicit damping equality, one can compute the first-order approximate stabilizing feedback of this form here. In this simulation, we considered a comparison between the proposed first-order controller, represented by a dashed line in yellow, and the standard emulation controller, represented by a dashed line in blue. Setting the desired configuration as pi over 2 and a sampling period of delta equal 1 second, we notice that the proposed controller approaches significantly in both the continuous time trajectories and the desired Hamiltonian function, so preserving the passivity condition at each sampling instant. On the contrary, the emulated feedback suffers the step size of the sampling period of delta of 1 second and thus is not able to match neither the desired Hamiltonian function nor to stabilize the pendulum at the desired equilibrium point. So just to summarize what we have seen today, in this presentation we have seen that feedback passivation in continuous time implies feedback passivation under sampling with the same target storage but with respect to a new output mapping which depends both on delta and the new control input V. The provided solution is based on the input SD matching, providing digital control matching at all the sampling instance the energy dissipation along the ideal continuous time closed loop dynamics. As we have shown in the paper, when considering post-Hamiltonian dynamics, feedback passivation is instrumental to properly discuss stabilization through energy management. In that case, in approximate sense, the input HD matching based feedback assigns a sample data port Hamiltonian structure proposed in reference 7 in O delta cube. Finally, feedback passivation is instrumental to several sample data methodologies such as backstepping in reference 5, feed forwarding in reference 6, and many other passivity-based control designs. This strategy opens a wide variety of applications as digital control is nowadays an unavoidable design requirement. Thank you all for today. I'm pleased to answer your question in the next couple of minutes or by email. Thank you all and thank you for your attention.